Hi, good morning, everyone. Maybe good afternoon in some places around the world. Welcome back to the Runtime Verification 2021. It's my great pleasure to introduce our invited speaker today is Professor Radu Grosu, who is a full professor and the head of the Cyber Physical System Division of the Computer Engineering Institute at the Faculty of Informatics at the TU Wien. It's also called Vienna University of Technology, right? Yeah. At Austria. Radu is also a research professor at the Department of Computer Science of the State University of New York at Stony Brook, USA. And his research interests include the modeling, analysis, and the control of cyber-physical systems and of biology systems. The application focus includes smart mobility, Industry 4.0, smart buildings, smart agriculture, smart healthcare, smart cities, IoT, cardiac and neural networks, and genetic regular networks. So Radu is the recipient of the National Science Foundation Career Award, the State University of New York Research Foundation Promising Inventor Award, the Association for Computer Machinery Service Award, and is an elected member of the International Federation for Information Processing Working Group 2.2. So without further ado, let's welcome Professor Radu Grosu to deliver the keynote speak for today.
Thank you very much, Lou. Thank you very much, Dana. It's a great pleasure to be here with you. And I'm going to share my screen, and so I see that I have to share sound. I think some of the results of the talk address a question that was long asked by the runtime verification community. Can we go beyond runtime verification? So can we do, for example, control? And now, I'm not claiming that what we are doing is ensured to be correct, but what we are doing at least allows you to learn from the monitoring process. So I'm going to talk about neural circuit policy enabling auditable autonomy. All right, so our inspiration comes for a small worm called C. elegans. Actually, this worm was investigated at Weizmann before, because it's a very small, 1 millimeter length, 0.01 millimeter width. It's translucent. It has precisely 302 non-spiking neurons. This is interesting because it gives me a link to artificial neurons. It has around 8,000 synapses, actually precisely 8,000 synapses. And it has precisely 95 body wall muscles, which are the actuators of the worm. You can see what kind of feats it can do while trying to eat. And it is, although it has that few neurons and synapses, it's able to do associative learning. It's able to do social behavior, and its connectome is fully mapped. I mean, this was one reason why it was studied before. The funny thing is that working with the biologists, we realized that for them, this is the model. Okay, so because they can produce this reliably all the time, you know, and our mathematical models, they said, oh, they are totally wrong. I mean, they are not good. Okay, but we said, all right, they are not good, but we can at least do something with them. We can simulate them. So looking at, actually, originally we looked at the heart cells and we were modeling heart cells, and then we switched to neurons, to these neurons of C. elegans, because they are very much the same. Okay, so they have a membrane which is fat because cells developed in sea ocean, and it was too salty out there. So they say, okay, let's keep the salt outside, salt being sodium. Okay, so they developed this membrane, and they kept let's say, sodium and potassium essentially outside. And since this is fat, they are, from an electrical point of view, they play the role of capacitors. You have a difference of concentration between the inside and the outside. And as a consequence, you have a difference of potential, which I write here as VI. And now we know from electrical engineering that the capacitance times the derivative of the potential, the rate of change of the potential, is the sum of currents that pass through its membrane. Okay, and there are lots of currents that pass through it. I'm sorry for the noise. I am in a clean room at the airport, but from time to time we are told that we have to wear masks. Okay. So anyway, there are lots of channels, and through these channels you have currents passing by, and they contribute to the change of the potential. Okay. And there is also calcium buffering inside, which plays a very important role for the synapses. And there are pumps that restore the potential of the neurons and so on. So this is really a lot. I'm not sure, right now we are not able to model this and use this beneficially. The hope is that in the future we might be able to do that. For now, what we did, we applied a very well developed and classical method in the computer science, namely abstraction, if you want, approximation. Okay, so what we did, we removed almost everything, or if you want, we put in the leaking current that you can see over here, we put everything in the leaking current, everything that was not of interest for us. And of interest for us were the gap junctions, which are electrical synapses, and the chemical synapses. Okay, and then we got this much simpler equation. And then we wrote down the currents. Okay, so you have a leakage current, which is has a very simple linear form. So the conductance is multiplied with the resting potential minus the potential of the cell. So what happens is that this plays the role essentially of a controller. If you want, anybody knows what kind of controller is this? Anybody from electrical engineering or control theory? Oleg, what kind of controller is this? Do you know? Just checking if you are awake. All right, so this is a proportional control. Okay, so and the error is the difference between the resting potential and the potential of the neuron. So if nothing happens, as long as the resting potential is different from the potential of the neuron, you are going to have a current, and at the end, the cell is going to get its resting potential. Now, the gap junction is also very simple, or the electrical synapse. So it's really an opening between two cells, and ion can pass from one cell to another, driving a current this way. And the equation is just the Ohm's equation. So you have a conductance between the two cells, between J and I. J is the presynaptic neuron, I is the postsynaptic neuron, and this gets multiplied with the difference of potential between the two. You can look at this also as a proportional controller, where the proportionality constant is the conductance between the two. Now, so far, my equation is linear. All right, so if we used only these currents, we wouldn't be able to model nonlinear systems. Okay, so now the action and the interesting part comes into the chemical synapse, which is really very complicated. So you have bubbles that are filled up in the nucleus with neurotransmitters. They propagate to the synapse, they bind to the synapse, they open, release neurotransmitters, and these neurotransmitters go and bind to the receptors of these channels that you see here. And then you either have potassium flowing in or you have chlorine flowing out, okay? And you can model this with differential equations. And in fact, I have a student that tries to see if this brings any advantage, or you can use a steady state equation. So what you can say is that you have a maximum conductance, GS, JI, and that gets multiplied with the conductance that is a variable. And that conductance really depends on the presynaptic voltage. Please let me know if you cannot hear me, because I hear my computer is starting making noise. So maybe I should at some point shut down my video camera, but let me know about it. So give me some feedback.
The voice is all good so far.
All right, all right. Okay, so So what can you have, as I said, and this actually, so this is actually the conductance, and this gets multiplied with the difference of potential. And this ESIJ is chosen such that it's either positive, the difference is either positive for activating when potassium flows in, or it is negative if you have an inhibiting current, okay, if the synapse is inhibiting, which is the case for chlorine, okay. Now, I want to mention that all these conductances, the leaking potential and this ESJI are things that you want to learn, okay, so they are parameters that you want to learn, okay, so you can have inhibiting synapses where chlorine flows out. And what was for me extremely interesting was that replacing the differential equation with the steady state equation led the biologists to the same equation that is used for neurons in artificial neural networks, to a sigmoidal relation. Okay, actually you can have also a variance here, multiplying the difference between the potential, the postsynaptic neuron potential and the mean. Okay, so you have a mean mu j. Now this mean you would like also to learn, and the same for the variance. So these are the equations, okay? And now in good tradition of genetic regulatory networks, we looked at the binary relation first. And we observed that you can have the same thing you have in genetic regulatory networks. You have activation, inhibition, and then you have more. Actually, there is a lot of interesting work that was done in Israel. Uri Alon did a lot of work on patterns or motifs, okay? And the simplest motive is activation. So when X goes up, Y goes up. Then you can have the next one is inhibition. When X goes high, Y goes low. And you can have coupling, which corresponds to an electric current, to an electric synapse, to a gap junction, okay? Now, the more interesting ones, and actually they are everywhere in nature, are the recurrent ones. For example, you can have activation from X to Y and inhibition from Y to X. So the idea is that X goes first. Now, typically, as I'm going to show you, Y might have an additional condition. So when Y goes on, it inhibits X. You know, the point is that these networks are really, so this is a, let's say, a programming paradigm that is parallel by default. And in order to have something interesting like sequencing, you need to impose it in this parallel framework. So you have essentially thousands of differential equations. They are all integrated at the same time, okay? And you cannot stop, say, but you know, I don't want to integrate these differential equations. You have to integrate them all, but you have to stop them working, okay? Another nice motif is the conservation, or if you want fault tolerance. So X activates Y, Y activates X. So they act actually as a unit, okay? And so you can replace one neuron with 10, with 100, depending on how much redundancy you want to have in your system, fault tolerance, if you want. And finally, another interesting binary motif is inhibition. X inhibits Y, Y inhibits X, and you can see that when X goes high, Y goes low, and the other way around. So it's like a flip-flop, okay? But it's an analog flip-flop, and it's done by neurons, okay? So this way you can implement, if you want, state machines, okay? Let me give you an example of what you can do with this. So suppose you have a guard. Suppose you have an expression like theta is greater than X. Now, all of you that have taken the class in compilers know that you can create an abstract syntax tree for it, where this node is the greater than node, and you have theta and X. Let's say theta is a threshold and X is an input, and you want to compare X to that threshold, okay? Now with neurons, what can you do? So you can say, I have sensory neurons, and one of the sensory neurons is bound to a threshold theta. Actually, theta is generally going to be a parameter that you might want to learn. And X is an input, for example, the position of a car. And then you are going to introduce an interneuron to compute the expression theta greater than X. Okay, so you can train it. So this is, if you want, a program scheme. So it's not really a program because you have these synapses. So you have two gap junctions here from the input to the interneuron. And you have then an activation from the interneuron to the next neuron, and they have parameters. So in order to make something out of this, you have to learn the parameters such that it works the way you want. And making them working the way you want might require reinforcement learning or supervised learning. All right. Now, the only place where, and that we observe actually in nature, so you can think that interneuron compute complex expressions that depend on the input. They can depend also on the rest through the actuators, but the loop is not inside, okay? So here, and the recurrence, let's say the command structure or the program structure is in this command neuron. So here is where you have recurrent relations. And you can see that X activates, the first one activates the second one and the second one. So this is the sequencing pattern that I was talking before. And in this sequencing pattern, the second neuron doesn't, as long as the first condition is not true, it's not going to work. Okay, so the first neuron remains active. So you can think of this first neuron repeating, having a sort of a while loop while theta less than X. Okay, and while theta is less than X, the first neuron can activate a motor neuron, for example, telling the motor neuron to go back. Now, in a while loop, you typically have also, even in the guard of the while loop, you might have conditions that depend on the body of the while loop. Now, in this case, you have conditions that depend on the body, but the effect is indirect because you activate the motor neurons, and activating the motor neurons changes your position. Okay, so it changes the value of the input of the sensory neurons. So this is very nice because you can have these conditions where you would have some kind of feedback. You can break them down in very simple feed-forward networks for the interneurons for computing expressions, in a recurrent structure for the command neurons, and then again a feed-forward structure for motor neurons. Okay, so essentially you keep the recurrence, the feedback, you keep it among the command neurons, and this simplifies the design. So now what can you do with this? For example, I have a student, a master student, actually he did it in master, and a PhD student together. So they worked on this and they implemented a parallel parking algorithm. So here you see this sequencing pattern. So this goes first, then this goes, then this goes, then, and we added also self loops because we figure out the addition of self loops allows you to strengthen the sequentialization. Now, the main idea was that we have 6 motion primitives. You go first back, then you go back and turn, and then you go down, and then you go back and turn, and then you go back, and then you stop. So you can see here, so that this first neuron goes back. So this is the motor neuron saying go back. The second, when it gets active, and this is a guard here, essentially saying something like, okay, I reached a point where I should start turning. This is the condition. So this is an input of position, and this is like a theta parameter where I am. And this neuron activates turn left and go back. And at the same time, it inhibits turn right. And then you have the next go back, then you have go back and turn right, again go back, and then you have a motor neuron that says stop. So this is actually a program scheme. So all these synapses have to be learned, their parameters. And how did we learn it? By using supervised learning. Okay, so we apply supervised learning. So we had a trajectory that we wanted the car to pursue. And based on that trajectory, on the input output, so where I am, what is the action, and so on, we learned the parameters of this parking trajectory. Now, another thing that, by the way, if you have any questions, ask me during my talk. I mean, don't wait up to the end, because at the end I might go pretty fast because I'm going to have to catch a plane. You can add also safety to it. So we have 3 sensories for moving backwards. We have a backward left, backward right. And these sensory neurons are combined together by these interneurons, and these interneurons are blocking all the movement in case you have an obstacle. You have, similarly, you can make it hierarchical. You have a forward moving portion where you have also a sensor if you have an obstacle in front, and this is blocking the movement that goes forward. So this way you can create actually in a hierarchical fashion a program scheme. Okay, so it's not really a program. So you have to train it with supervised learning. As long as we didn't use TensorFlow or more advanced genetic algorithms, we were not able to create what we wanted. So this is what I'm saying. You know, all your monitoring that you have done before, you can use and actually you can impose even safe behavior with learning. So I think the dream of getting from runtime verification to control is by really doing either supervised or reinforcement learning. Okay, so you either give it, you know, you monitor a reward, or you monitor which is very abstract, or you monitor something simpler, which is the input and the output signals in the system. Now, if you put all this together, you get this. It looks like a state machine. It's moving forward. This is the motor neuron. So now it's an obstacle in front of it. It stops. Now it continues moving forward. It actuates moving forward. And now it gets obstacles behind. So these sensory neurons are active. So it stops the movement. And now it moves back, you can see. And now it moves back and turns left and inhibits turning right. Then it starts going back again. Then it goes back and turns right. And then it goes back again, and at the end it's going to stop. So it really looks like a state machine, and it's understandable. You can say what it can do, all right? And here we have a video of the car moving, and we show that actually you could be at various distances to the wall, and you are still going to get a reliable parking. So these are were done in my lab. All right, so after we did this, we also looked at how noise is propagating, and we realized that because you have a capacitor equation, you have RC filters, which are low-pass filters, and they actually, if you put noise in the sensory neurons, this noise gets actually a little bit reduced by the interneurons, even more by the command neurons, and when it reaches the motor neurons, the noise is gone. And we also looked at classic recurrent neural networks, and we realized that actually the noise is passing all over, you know, and that was one reason why we were saying, okay, this was observed not for RNNs, but was observed for image recognition, where you put a sticker on a sign that says stop, and then actually what the machine does says, okay, it's drive by 30. So we were very happy with this, but people starting asking us, all right, so now that's easy. Are you rediscovering the wheel of machine learning? This is a very simple thing that you have done. Can you do things that are more complicated? And at that time, Alexander Amini from Daniela Ra's group implemented an end-to-end controller that looks like that. So you had the camera stream, and that camera stream was taken and applied with 5 convolutional layers to get features from the camera stream. And then the control itself was done with 1,400 neurons and around 4 million synapses. And this was actually done for lane keeping. So you had only, let's say, one motor neuron responsible for turning left or turning right, okay? And here you can see also the attention map. So this is actually, when you go backwards, you want to look when these decisions were taken for the motor neuron, where was actually this network looking at? So what were they attending? So this attention map is going to be very important. All right, so we knew about this work, and then I sent Ramin and Matthias. So Ramin was my PhD student, and Matthias was my master's student at the time. We sent them to Daniela. Okay. We also talked to Tom quite a bit, and actually Matthias is now working with Tom, and Ramin is working with Daniela. This is what we thought. Okay, so we took only 4 convolutional layers, which gave us 32 features. So we said, okay, these 32 features are our sensory neurons. Okay. By the way, the convolutional networks are kind of explainable. So that's the best you can get, at least in vision, because they identify small features at the beginning, then bigger features, and so on. So these 32 sensory neurons were giving us some features of the image. Here you see, by the way, the map. And then the question was, what are the interneurons? So we found out that we need 12 interneurons. We had no idea actually how many there should be at the beginning. But we had a pretty good idea that we would like to have 6 command neurons. And I'm going to tell you what they are doing, and 1 motor neurons. Another thing where we did experiments was the sparsity. So for example, we have a framework created by Matthias and Ramin called NCPs. You can find it online. And they allow us to say, you know, what amount of synapses you want to have for a particular neuron. So here, for example, we were saying we would like in general to have 3 activations and 1 inhibition. Actually, these are also parameters, hyperparameters. You have to play with them and to see how it works. And then we had the motor neurons, and we had by some default connections that I'm going to talk about. And then we had the synapses from the interneurons. As I said, interneurons compute expressions. If you want, they compute correlations among the features. And then the command neurons activate this 1 motor neuron. So each of them has a synapse to the motor neuron. Again, this is a program scheme. And the idea we had, again, the easiest way to understand what these new networks are doing, we call them neural circuit policies, are the command neurons. And for this, we said, okay, I need the 1 neuron to turn slightly left, 1 that turns stronger left, and 1 that turns very strong left, and another 1 that turns slightly right, stronger right, and very strong right. Okay. Now we know that turning left and turning right should inhibit each other. So we had connections between them. So left, right, and so they should have inhibitions, and the other way around. Okay. Because you cannot turn both left and right. So they should inhibit each other. And the rest was how many synapses should come from the interneurons to the command neurons. How many of them should be really here. Okay. Okay, so this was again the program scheme. And what we did, so my students drove on the streets of Boston and collected actions and state from the car. And based on that, we did supervised learning. So we used TensorFlow, lots of hours of TensorFlow. What you should observe here is also very nice. So you can see, without doing anything specific, the attention is really concentrated where an experienced driver normally does. So it's really at the front of where you're driving. Okay, so the result of this work was very nicely packaged by MIT, and you're going to see a short video now. This is Matthias, by the way. Yeah, so you saw how it works. So this work was published in Nature Machine Intelligence. So now you see that it was not a lie that I'm combining biology with computer science. And what you can take as a message is that you could learn from scratch the whole stuff. Actually, you don't have to learn it the way we do, but I think that the future is really in having some design and some learning. And for example, convolutional neural networks are very successful because they have an architectural understanding. They are a particular pattern. And I really believe that in the future, we are going to have building blocks based on neural motifs that we are going to put together and then do the machine learning. Now, let's look at what MIT had before I sent my students. So this is the convolutional neural network that you have no chance to understand. And then look at the attention map. Look where it is looking. It's really scary. I mean, I wouldn't let a car like this drive me on the streets of Boston, and moreover, it's going to get now in a curve. So since it's doesn't know really where to focus its attention, it's going to get out of the road. Okay, so in this curve precisely now, it's getting out, and then it has to move back on the road. Okay, so it's really, I mean, it's looking really outside the road instead of looking at the road. So this end-to-end version that was done by MIT with Toyota is really pretty clearly, in my opinion, not the best choice you can have. But then we looked at recurrent neural networks because actually, the architecture, the controller itself has to be recurrent. And here you can see a continuous time recurrent neural network, and you can see its attention map again. And so you have 64 neurons in this case, but you have no idea what they are doing. Okay, so that was learned from scratch. Okay, and they have the same problem getting out of the road in this curve. And you have the problem that you don't understand them. So the point is that if you have no guidance in your synthesis process, no matter what you synthesize automata, you synthesize program, whatever you synthesize, if you don't have any guidance, you are going to synthesize a bad controller, a bad program, and you're not going to have any idea what it does. All right. Now, this one is actually the best one among the competition, which is the state-of-the-art recurrent neural network. So these are the long short-term memory networks, LSTMs. And you can see that the attention map is much better, so it's really focused on the road. But it also looks too much outside. Okay, now this might be an artifact that we put too many neurons. We gave it too much capacity. So you saw it went out of the road. So it had trouble. And also, but again, as before, you have no understanding what it does. I mean, you look here and say, all right, I have no idea what it does. Should I trust it? In my opinion, you shouldn't. So unless you understand it, you should never trust it. Okay. Maybe you can verify it. So actually, we do work in verification too. So that's something we are working on to verify these neural networks. Now let's add some noise. I mean, look at this. I mean, the original network. So this noise, imagine, it could be rain, like the way we showed it before. This Gaussian noise. If you look at the attention map, you realize that this network is looking everywhere and nowhere. It has no attention. So it's really, really, really problematic. Now let's look at CTRNN's attention. It's also a disaster. I mean, really scary. I mean, don't let the autonomous car, at least that use machine learning, drive you on rain or fog or snow. Forget about it. Don't let it do it. And now with LSTMs, again, this is kind of the best from all of them. So you see, you kind of can see where it is, but it's looking again too much outside the road. So it's looking outside. Now it went outside the road. It missed the curve. And now it starts to look more on the road, okay? But it's still scary. You don't know what it does, and it's still scary to drive it. All right, so this finishes my discussion about the noise. One very pleasing result of this work was that it was nominated among the 10 most influential innovations in 2021, and It was listed by the UNESCO NetExplo forum, and that put us with the worm driver together with other work. And for me, it was kind of very nice that we were put together, for example, with the biggest quantum computer developed in China. All right, so I thought, okay, that guy's really put a lot of money and a lot of work to create a quantum computer, and we are on the same list with them. So that means that we are pretty good, or we left a good impression. Now let me talk in the, so how much time I still have, like, let's say like in 5 minutes, let's see what is the structure of deep neural networks and how do we compare to them. So an artificial neuron looks like this. So it sums up a set of inputs multiplied, weighted by the weights, and then it passes through a nonlinear function, which is a sigmoid or a ReLU or whatever you want, hyperbolic tangent, and it gives the output. And this is the equation that you want. Now, this model is wrong from a biological perspective. But the funny thing is that because this is not what does a neuron, and the idea was, related to spiking, and actually this sigmoid is not spiking. So the error was that they didn't distinguish between neurons, which are the summations, and the synapses, which are the sigma. Now, the funny thing is that their synapses were also wrong. And when you put them together, the network expression was almost right. Okay, so this is why neural networks actually work. But they are not a current model, they are a conductance model. Okay. And I'm going to tell you why. So you can think of the you can think of Y as a sort of currents, but they are not really currents because you have Y is not Y is not a current. Okay, and Xi. That's why you cannot think of it as a potential. So actually, when we developed our networks, we had no idea whatsoever how they compare to artificial neural networks, and we were just saying, they are wrong, and the people were getting upset and saying, why are you saying that? You are wrong. And then the next step to understanding what we are doing were residual networks, which opened up a neuron, and they were passing the information from, let's say, from one class to another as an identity, because they realized that they cannot model properly with nonlinear functions identities. And so now they split the summation and they gave it a name. So they say xi plus 1 is xi plus the sum, and then the output actually is y. Whereas before, you just have this y as a single neuron. Now, if you look at this equation, you realize that actually this is the discrete form of a differential equation where dt is 1. So you just have to move xi to the left, and you have delta x, and then you divide it by delta t, which you make 1, and you got a differential equation. And this is what people observed in neural ODEs. And also CTRNNs had a similar form. Now, don't write it in differential form to show the relation to the original one. So here you have xi at t plus 1 is xi of t plus a leaking current, sort of a leaking current, okay? And then you have a sum. If you want, you have a sum of conductances, okay? So, the question is, what is the integral of a conductance? Okay, the integral of a current is a voltage, but the integral of conductance is not really a voltage, okay? So our NCPs, we also call these neurons, when we talk about neurons, liquid time constant neural networks. So here the difference you're going to see. So now these YLIs, they are currents, and XI is going to be a potential, okay? So now you see WLI is a constant, and this gets multiplied with the difference of potential. So I write X for potential, and I write Y for current. And then the current is really the sigmoid, which is, let's say, a conductance, a varying conductance, multiplied with the difference of potential. So our model is really electric, so it has a biological interpretation, whereas the models of artificial neural networks, they don't really, because they lack this multiplication of a conductance with the difference of potential. Okay. Now, what are the main characteristics of our network? One nice thing from the control point of view is that we have a linear model because of multiplication with xi here and here. So it's a linear model, but with state-dependent coefficients like you have here. So you can use the theory for state-dependent Riccati equations to solve this actually very nicely. Another thing is that the nonlinearity is associated to each synapse independently and not to the neurons, like in classical neural networks. And as a consequence, we can pack more parameters for the same number of neurons and synapses. Let me tell you what I'm talking about. Let me show you. So here, every neuron is the plus here. And for every neuron, you have only one synapse. And from that synapse, then you multiply with different weights. Okay. This works like ReLUs. I mean, for ReLUs would be fine, but ReLUs are not good for control. Now, what we do is we associate to every synapse a different sigmoid. Okay, so every sigmoid has its own variance and mu, and you can learn them separately. So there is no reason why all the synapses going out from a neuron should be the same. Okay, they can be different. All right, and they can learn different things. Now, this is how you can draw it, but you can draw it also this way. You say I have neurons and I have synapses, and we think that the complexity of a neuron is really in this: how many neurons you have and how many synapses. If you make more powerful synapses, you don't have any disadvantage in terms of understanding. So this is why actually we can pack much more behavior with much smaller networks. Okay, so packing more parameters reduces the size of the network, and you can claim that the approximation capability of a network is really correlated, strongly correlated to the number of parameters that you can learn. All right, so we use this kind of work, for example, to the Grand Prix. Last year it was purely virtual, and we were very happy. We were teaching for the first time autonomous racing cars class. We got the slides from Raul, and we were very happy that we can, and actually also the prints, how we should build the cars, okay? And this was the team at that time, and this is a racing car that you can see. It is really, it's F110, so it's 1/10 of the size of an F1 racing car. And it has LiDAR, it has cameras, everything. It has a very powerful GPU, and has very powerful actuators. Actually, you can drive up to 100 kilometers per hour with them. And this year, we were very happy that to be able to defend our first place, but this time with real cars. So actually, I have a beautiful video, but I don't want to put it here. So, and this is the team that defended our title in Prague at the Aeros conference. And you see, we were kind of the richest team there, so because we had a lot of cars. So I got, fortunately, funding for buying these cars, and I could. So one of them got trashed there, so it was good that we had a replacement. All right, so with this, I finished my presentation. So I left 15 minutes for you guys to ask questions. So please ask questions. You haven't asked them at the beginning. So Oleg, please go ahead.
So I like the idea of these neural policies. My question is, if you are building a complex system with many different policies, can there be, interference between them, or some other undesirable effects?
That's a good question. So for example, in the parking application, so we had several policies. Okay, so we had safety policies combined with, so this was the safety when you go backwards, and this was the safety when you go forwards. This was the forward moving. Okay, they were in sequential composition with each other. And so, yeah, so the question is, how do you combine them? So I think one way to combine them might be by using this fault tolerance motif, where you have two neurons, activation, and that could be like a shared variable where you share the work between them, Now, are they going to influence? Here, they didn't influence each other because they, one advantage is if they only act on the, actually they influence each other, in fact, here, because you see, when you have an obstacle, the motor neurons are blocked. And as a consequence, the policy of moving forward is stopped. Okay, so actually it works, but it pauses, all right? The same here. If you put an obstacle in front of the car, it stops the moving forward policy that you have right here, you know. So obviously, so the trick is actually how to, first the question is, should you design this or not? Okay, that's a good question. So we are kind of advocating designing stuff on your own because then you understand them better, but you can learn them from scratch. Now, one interesting work by Joshua Benjo is so-called recurrent independent machines, RIM, where you want to have an inductive bias in learning independent components. And the main idea there is that you use attention to figure out, and the state of your so-called independent components, you kind of have to have an idea how many independent components you have. So use the attention. So attention is a correlation between the input and your state. And that attention tries to figure out this input that I got right now to which component is interested in. Okay, and you try to decouple them as much as possible. Now, the ones that are not interested, they are going to idle, and the other ones are going to do something. And then you have a broadcasting mechanism that shares the information to everybody else, and then you get to the next state. Okay, and that this kind of structure you can already impose in your machine learning algorithm, such that you have an inductive bias for learning independence and hierarchy. Okay. So you either have something that you design, and but then you know very well how they interfere, and here you see how they interfere, because they, you know, here you were moving backwards and it sees an obstacle, it stops, you know, it pauses. But the very moment you remove this part, the obstacle, then it continues working from where it left. Okay. You achieve this by, for example, by connecting the policies through the motor neurons. Okay. And yeah, I think this is interesting to figure out. Some other policy might influence each other. Actually, I have another one, which is kind of interesting. So let me show you where actually you have concurrency. So where is, okay, so give me a second. Ah, I know. So because of you guys, I have trouble, you know, finding my clicks here because they are hidden. Okay, so all right, so I have a long version of this. Now let me show you another thing that we learned, you know, which is kind of interesting, a controller. All right, so it's going to take some time. All right, this is what I wanted to show you. So here you have a robotic arm, and this has 7 joints, and it has sensory for moving left, moving right, and it has actuation, move left, move right, every joint, these joints that you have. And you have a policy that says, oh, I'm starting in a parking position. I go to the grab position. So this is the next neuron. Then I grab a ball, I move it to the bring position, and then I come back to the park position. So this is this policy. Now, in parallel with this policy, you have to control this open and close, the grabbing part of the arm. And this grabbing part you kind of put in parallel. So you activate opening or grabbing and opening when you reach the put position. Then you open it later on, and then you come back. So you have 2 policies, actually, the grabbing of the ball and the moving and parking that kind of go in parallel with each other. And again, here we learned the structure. We had no idea how many interneurons we should have. We figure out we need 2 layers, and it's again just feed forward. And we had no idea how to control this. We just learned it by experiments. And if you look how it works like this. All right, so now we don't do the grabbing here because for some reasons in the simulation you couldn't open and close properly the arm there, but you see how and you have this sequential policy again. Now I think this is very interesting. Probably, you know, as you saw, they interfere. Now the question is that interference desired or not? but you might control it.
Thanks. I have more questions, but I want to let others speak up.
All right, so please go ahead, guys.
So Radu, it's very impressive work. I really like all the demo videos you showed. So I noticed that the one you showed in the Boston, the demo, it's a lane keeping system. So there is basically no other cars in the road or no pedestrians or others. But you also have showed just now that this neural policy can actually work with different like parking or these robot applications. So I'm wondering, so if we want to go from applying to lane keeping to maybe slightly more complex environment in the driving scenario, like if you put some pedestrians or other cars, which we can't really predict where they will be. So what it takes? Does it need to like redesign your architecture or just to collect more data, do more training? So what?
I mean the pedestrians, you can all the stuff with pedestrians, you can actually model the way I showed you here, so adding a safety mechanism, so this was a safety mechanism that we put on top of what you were doing before. So if somebody jumps in front of your car, now obviously you need a very good vision mechanism there, because you have to detect. I mean, it doesn't really matter what jumps in front of you. You might want to stop. So as you can see here, you can do this kind of in a modular fashion. People don't do this right now in modular fashion, but I think this is a mistake. So I think you can do it in modular fashion. Now, driving more lanes, it's kind of interesting. So this is something. So actually in F110, you try to overcome the other, but the problem is in the race itself, we didn't do this to overtake. We didn't do overtaking. So once we reached behind the guy in front of you, we drove right behind him without overtaking it, because we were winning anyway, because we had a better time. Okay. So, but in general, if you look at racings, you would like to overtake. Now that maneuvers, I mean, how do you add these maneuvers? That's actually a very interesting question, So I would prefer to do it in a modular fashion, or like also impose this modular fashion in the learning mechanism, And but that's something that we have to do. I mean, this is would be all very interesting work, But I think safety should be kind of simple, So it shouldn't be given only to data sets for training, Because if you have good sensors, you see what's in front, you immediately detect an object. That safety part, you can design it totally independently. So, for example, collision avoidance, you can make it as an independent part of. Now we haven't taken care of this in the lane keeping approach that we had done there. Because we don't have any sensors for for stopping or something like that, So it was a simple environment, but you can add that the same way we added to the parking.
So if you add more, like I actually quite like the idea of you do this in a modular way. The question is, if you add more modules in this architecture, then does it mean that you need to when you collect data and do the training, can you do it also modularly, like only do the collect data and train for the new added module, or do you need to do it all over again?
That's a very good question. We are getting to assume guarantee. You're right. I mean, the question is, the module that you are testing, does it depend on the inputs from the other modules, okay? Or is it totally free as an input? And I think that for this here, you can assume that it's kind of free. I mean, it's really, somebody can jump in front of you. So you could test it completely and learn it totally independent, okay? Now, in other situations, when you put things together, they might have feedback among them. And then you get into the assume guarantee, which is probably, it's kind of would be nice, especially if you want to do proofs, to do it modularly. Probably you won't be able, I mean, we know assume guarantee, I think, for 20 or 30 years, and it's still the best you can do for verification. But it's tough to implement. Now, what you can do, actually, all these dependencies, when you put things together and you test them, but again, you need labels, you know. So, but you can do that with simulation data. So you can do lots of stuff in simulation and then do a lot of training. The question is, what can you guarantee about them, you know, when you put them together, you know? And yeah, the answer is that probably less. I mean, yeah, I mean, unless you test the entire network, but that most likely is going to blow up your, you know, your verification tool. So we are still there where we were 30 years ago. It's only that we can, you know, devise things somewhat faster, and we can use the monitoring, the runtime monitoring. I mean, everything here. I mean, to create all these data sets that you use for machine learning is really runtime verification. You can learn whatever you want from runtime. You know, you can monitor whatever things that you think are important. You know, like you can define your own events that you are monitoring, and you can use these events in your machine learning, and you put them in the machine learning component. And, I think this is, I hope that Klaus would be here and listen to me. I don't know where he's here, Klaus Havelund, because he was thinking about this. Ah, Klaus, you are there. Hi, Klaus.
Hello.
So do you see your dream come true, or you don't see it at all?
Of course.
All right. Anyway, I mean, again, guarantees. Can you give guarantees? I think without verification, you can't. You know, ultimate guarantees. I mean, you need some other techniques to prove that things work properly, or you need a good assume guarantee framework. All right. More questions? Your last question, Oleg, if nobody jumps in.
Actually, let me talk to you offline. I think I have, it's more of a suggestion rather than question. So it's going to take time. Let's talk when you finish your travel.
All right. All right. So I'll send you an email.
Thanks.
Okay, guys. So actually the boarding is in 10 minutes. So I should better stop here and go to board. Otherwise, I'm going to lose my plane. So again, it was a great pleasure being here. Thank you very, very much for inviting me. And I hope I provide you some inspiration. And also, I wouldn't mind also criticism, you know, because that's how you go ahead, by listening also to criticism. So send me emails if you want to criticize or have any ideas. Thanks a lot.
Okay, thank you.
Bye.
Let's thank Radu for the wonderful talk.